I'm here at Innovation Day with my colleague Monty Barlow. Monty is our head of strategic technology. Plenty in that. Hi, Monty.
Hi, Richard.
Hi. So today you've been talking about quantum. So let's focus our conversation on that. First of all, touch on the mystical, the terrifying elements of this. Should we be scared here? You know, how tractable is this?
I don't think we should be scared, but it is going to bring some fairly big changes in some applications. Quantum computers will weaken cryptography in use today, but there's already, say, quantum-proof approaches being developed. So it's just going to mean change, I think, rather than anything scary.
So if I understand your role correctly, you're taking some of the long-term bets, the long-term investments that will help support our client work in the future. Is that about right?
Sure, absolutely.
Okay, quantum fits in there?
Yes, quantum does. It's an area that's suddenly starting to explode for a whole number of different reasons. Just a sheer demand for it, discoveries are being made, and that's fueling investment from companies and governments that's pushing everything ever quicker. And meanwhile, core pieces of science, like how you can manipulate a particle and hold it in a particular state for a long time, are improving rapidly as well. So the kind of toolbox with which you can build quantum systems is improving the whole time.
Sure. So what have we been up to? I understand there have been various sort of investment projects going on. What's happening?
Sure. So probably worth taking a step back and saying that quantum revolution that's happening right now you can arrange in a few different areas. So there's quantum compute, I think a lot of people are aware of. It's the commonly spoken about one. It promises one day super fast exponential speed ups in a lot of scientific and other applications. But perhaps less spoken about are improvements in sensing and improvements in communications and security. We've got an interest in all three areas. So for example, in sensing, we're building practical magnetometers. Those are devices that let you measure a magnetic field 1,000 times smaller than you can do in conventional ways. That in the future could mean an MRI scanner that today has massive magnets and cryo-cooling and other things around it becomes a portable, easy thing to take out into the field or for working with people who can't, for example, go in an MRI scanner. If we look at communications, a big area of investment for us is quantum key distribution. The idea here is that no matter how secure your encryption scheme is, if somebody knows your keys, they can decrypt the data and you don't want them to. The analogy I would use is it's like somebody taking a copy of your front door key. No matter how secure the lock is, how powerful the lock, if somebody has a copy of the key, you have no security. So with quantum key distribution, we're building some really robust and practical ways of sharing keys and knowing that nobody was listening in.
So what's the property of quantum mechanics that underpins that as a technique?
Oh, there's a few properties, but a simple one, for example, is that you can't make a measurement without affecting a system. So we can arrange things so that the eavesdropper, in attempting just to listen to a single photon of light, will leave a trace, an indelible trace that proves later that they listened in on our communications, and that we can't therefore trust any keys we exchanged.
Right. So this is an area of active research and investment. How far away is this from something that could be deployable in the field somewhere?
It's deployable today, but at a cost and complexity that might make it prohibitive. What's attractive in QKD, for example, for us, the key distribution, is that a lot of the approaches being taken in radio, in things like error coding, and that make 5G robust, for example, can be applied to the optics as well needed in quantum key distribution. So we are hoping to drive this through to much more commercially useful systems in very few years, I would say.
There's often a hype cycle associated with emergent technologies. I know there was a fairly major announcement of a step on the way towards a quantum computer a few months back. You know, what's the hype cycle doing to all this? Is this real and now, or is there more hype than reality, do you think?
I think it's probably fair to say it depends which area we're looking in. compute is probably the most hyped. So we've had claims this year of so-called quantum supremacy, which is saying that a quantum computer for the first time has been able to equal a classical computer at a very carefully chosen task. Even that has questions about it, but that's not a comparison that's particularly useful. Quantum computers in their general form might be decades away from normal commercial use.
How can a person assess what's real and what's not real as they're paying attention to developments in quantum? That's my question. You know, as a non-expert, what can you do to really understand the reality of genuine progress?
Personally, I like to see some kind of proof or comparison. That ideally is peer-reviewed or that other parties in some way believe in. So there has been progress in quantum compute, for example, this year. Whether it quite lives up to the hype is a question, but it's undeniable. There have been breakthroughs where people have managed to send entangled photons from satellites over thousands of kilometers and so on. That's real. There's no reason to believe that that's not happening. The subtlety often is around what difference that's going to make to applications in the near term. It's a big, complex area. It obviously has a almost 100-year history at this point in time. So there have been a lot of claims over that time, and it is going to take some time for some of these breakthroughs in science to filter their way through into engineering and into products.
How can you know? You've got a business challenge, you've got a thing you want to achieve. How could you know whether some property of quantum mechanics might help you solve this challenge? How can you move forward?
It is a good question, and of course in AI that's something we've been working with customers on. If you can find companies, organisations who have no axe to grind, who have no need to push an AI or a quantum agenda, who can simply look at the best approach to a problem, then you can get a fair answer. If you believe those trying to sell you artificial intelligence in a box, or in the future quantum in a box, they're always going to position that as the solution to your problems if you're not careful.
All right. Monty, thank you very much.
Thank you, Richard.